Imagine trying to map, say, every single island in an archipelago, but your satellite image is blurry, and new islands keep popping up while old ones sink.
Right, it's constantly shifting.
Exactly. It's a bit like astronomy sometimes. Numbers we thought we knew can change, well, dramatically.
They certainly can.
Okay, so today, let's unpack this. We're taking a deep dive into our own cosmic backyard, the Milky Way.
Our home galaxy.
And we want to understand how one specific piece of technology has just fundamentally changed our count of something pretty special. Open star clusters.
Mm-hmm.
Our mission here is to see how this new data reshaped everything, pulling insights from, well, quite a stack of recent research.
Yeah, there's been a lot happening. So maybe we should start with the basics. What is an open cluster?
Good idea. Lay it out for us.
Okay, so think of them as stellar siblings, groups of stars, typically maybe hundreds, sometimes thousands.
Right.
And they were all born from the same, giant molecular cloud. Because they share that origin, they're all roughly the same age.
Stellar siblings, I like that.
Yeah. And unlike the really dense globular clusters, these open clusters are, well, quite loosely bound by gravity.
Ah, okay, so they don't stick together forever.
Exactly. They slowly disperse. This happens over hundreds of millions, maybe up to a few billion years.
What causes them to drift apart?
Several things, actually. Radiation pressure from their own hot young stars can push them apart.
Right.
Close encounters with other stars or clouds can disrupt them. And just the general gravitational tugs as they orbit the galaxy play a role, too.
Makes sense.
But what's really remarkable, I think, is that they are still forming in our galaxy. Right now.
Seriously?
Yep. The estimate is maybe one new cluster every few thousand years or so.
Wow. Okay, so before this this game-changing mission we hinted at, what did we think we knew?
Well, historically, astronomers knew of, let's say, more than 1,000 open clusters. That was the ballpark figure.
More than 1,000, got it.
But there was always this suspicion, a feeling that maybe tens of thousands more might actually exist, just hidden from view.
Hidden how?
Well, that leads to the challenge. The catalog numbers back then were maybe around 3,000 or so, but counting them accurately, that was tough.
Why was it so hard? What was the core challenge?
The main issue before this mission's data was telling real clusters apart from fakes.
Fakes.
Yeah, essentially. Many previously identified clusters turned out to be just asterisms.
Asterisms.
Yeah.
Like the Big Dipper isn't a real cluster.
Exactly like that, just on a potentially denser scale. These weren't real gravitationally bound groups. They were just overdensities of stars that looked like they were together.
Right.
Maybe because of line-of-sight effects. A nearby star and a distant star just happening to align from our perspective.
That chance alignment.
Or sometimes patterns caused by dust blocking light, especially near the galactic bulge, could mimic a cluster. It's tricky.
So how many turned out to be these asterisms?
It was significant. There was a fascinating study, Kantak Godun and colleagues back in 2018. They looked really carefully at the big pre-mission catalogs, and they found that out of, I think, more than 3,000 identified clusters in those lists,
Yeah.
they could only really confirm about 1,200 as being actual, real open clusters.
Wait, only 1,200 out of over 3,000.
Yeah, less than half.
Wow. So more than half of what we thought were clusters
Yeah.
weren't. Okay, beyond just getting the number wrong, why does cleaning up that list matter so much scientifically? What's the bigger picture impact?
Oh, it's huge. Think about it. Weeding out those false positives, those asterisms, gives you a much cleaner sample of real clusters.
Right, a true sample.
And that cleaner sample suddenly lets your observations make more sense. For instance, the distribution of cluster ages, the cluster age function, it starts to match our theoretical models of how clusters form and dissolve much, much better.
So the theories were okay, the data was messy.
Precisely. And with the cleaner data, you see patterns emerge clearly, like the youngest clusters. They are tightly concentrated near the galactic plane, tracing the spiral arms exactly where you expect new stars to form.
The star factories.
The star factories. While the older clusters, they're more spread out, more uniformly distributed, often further from the plane, further from the galaxy's center. It paints a much clearer picture of galactic evolution.
Okay, that makes perfect sense. So this brings us neatly to the star of our deep dive.
Gaia.
The Gaia mission. Its data releases, especially early data release 3 and data release 3, have been absolutely pivotal.
It's transformative, really.
Can you remind us what Gaia actually measures?
Sure. Gaia provides incredibly precise astrometry, so that's the exact positions, motions, and distances through parallax for, well, an unbelievable number of stars.
How many?
The latest releases cover more than 1.8 billion stars across the galaxy.
1.8 billion. It's hard to even grasp that number.
It really is. And it's not just position, it's their 3D positions, their 3D motions through space, plus brightness information.
Okay, so Gaia starts delivering this unprecedented data. What happens to our cluster count? This is where it gets really interesting, right?
Oh, absolutely. It was an explosion, a deluge of new results, as Cantat Gaudin put it in 2022. It just completely transformed our ability to study these things.
So we went from that pre-Gaia figure, what was it, around 3,000 cataloged, maybe
Mm.
1,200 confirmed?
Yeah, roughly that order.
What's the number now?
Now, the current number stands at nearly 14,000.
14,000.
14,000 unique open clusters. And the vast, vast majority of these new ones, they've been discovered thanks to Gaia's precision.
That is just staggering. From maybe 1,200 confirmed to almost 14,000.
It really is. The jump is enormous. If you saw it on a graph plotting discoveries over time, the line just shoots vertically upwards around 2018 with Gaia DR2.
And how did researchers actually find all these, with 1.8 billion stars to sift through?
Well, that's where the power of the data meets clever techniques. People used all sorts of methods.
Like what?
Machine learning was a big one early on. With Gaia DR2, one group, Castor Gennard and collaborators, found 570 new clusters using machine learning algorithms trained to spot the characteristic patterns.
Wow.
Another team, Cantat Gaudin's group again, recorded over 2,000 with DR2.
2,000 in one go.
Well, in one study building on DR2, yeah. Then with EDR3, he and colleagues found another 836, including quite a few, like 46, at really high galactic latitudes, way above or below the main disk. That nearly tripled the number known up there.
So finding them even far from the plane.
Exactly. But perhaps the biggest single discovery haul came with DR3, a paper by Hunt and Reffert in 2023.
Okay, what did they find?
Get this. They used a blind all-sky search, basically telling their algorithm, go find cluster-like groups anywhere using something called the HDB-SCAN algorithm.
Yeah.
They found 6,272 new clusters.
6,000 in one paper.
6,272. It's just,
Yeah.
mind-boggling numbers. Shows the power of systematic, unbiased searching with this kind of data.
That's incredible. It really underscores how Gaia lets you see the clusters through the forest of foreground and background stars, doesn't it?
Absolutely. It cuts through the noise beautifully. There's a great example, actually. Neirola and colleagues, in 2021, they used Gaia DR2 data,
Okay.
and they identified this completely new, massive young cluster. It's about 2,300 parsecs away, so, reasonably distant, in the Sagittarius arm.
What was special about it?
Well, it contains more than 30 really bright stars, brighter than magnitude 13, and based on its stars, they inferred it must have been really massive when it formed maybe around 10,000 times the mass of our sun.
10,000 solar masses.
Yeah, one of the most massive young clusters relatively nearby. And before Gaia, finding something like that, buried in the dense star fields of the Sagittarius arm, incredibly difficult, maybe impossible. Gaia's precision in measuring which stars move together through space was key.
It pinpoints the actual family members, not just stars that look close together.
Precisely. It gives you their shared motion, their shared distance. That's the giveaway.
So with all this data pouring in, all these different discovery papers, it must become a bit chaotic trying to keep track.
Exactly. Different teams using slightly different methods, different criteria. You needed a way to bring it all together.
And that leads us to...
The culmination, really. This ambitious compilation by Perryman and colleagues in 2023, they created the Unified Cluster Catalog, or UCC.
The UCC. Okay, tell us about that.
Well, its significance is, it's basically the reference now. It is by far the largest catalog of open clusters in the Milky Way.
Attaining.
Almost 14,000 clusters, that number we mentioned earlier. It largely comes from this unified effort.
And how did they build it? Did they just list everything found?
No, it was much more rigorous. They went back to the source. Gaia DR3 data, looking at stars down to a G magnitude of 20, which is quite faint.
Okay.
And they used a specific, consistent probability algorithm. For every star near a potential cluster, they calculated the probability it was a true member.
Based on what?
Based on everything Gaia gives you. Its precise coordinates, its parallax, which tells you distance, and its proper motions, its movement across the sky. Crucially, they also factored in the uncertainties on all those measurements.
Very thorough.
Extremely. They started by gathering nearly 25,000 reported cluster candidates from all the previous catalogs and papers.
25,000?
Yeah, but then they did careful cross-matching, removing duplicates, applying their membership criteria consistently, and that reduced it down to the 13,684 unique open clusters in the final UCC.
13,684. Okay.
And for those clusters, they identified in total more than 1 million probable member stars.
1 million stars sorted into their cluster families. That's amazing. And for listeners who might be curious, is this catalog accessible?
Oh, yes, very much so. It's available online. The website is ucc.ar.
ucc.ar.
That's right. And it's got some great features. There's a zoomable sky map where you can see the clusters, you can select clusters, look at plots of their member stars, things like color magnitude diagrams, and get links to other databases like Simbad. It's quite intuitive.
Fantastic. So let's bring it all back then. What does this all mean? We've gone on quite a journey here.
We have.
It means, fundamentally, we've just taken this incredible leap in understanding and mapping our own galaxy's open clusters. We've gone from maybe a few thousand suspected, only about 1,200 confirmed pre-Gaia,
Right.
to now having a catalog of nearly 14,000, with over 1 million member stars identified. All thanks, really, to one mission.
Gaia's impact cannot be overstated here.
And for you listening, this deep dive, it's kind of a shortcut to seeing just how dynamic science is. How one new instrument, one flood of new, precise data can completely redraw the map.
It really reshapes our knowledge.
It's a powerful example, isn't it, how technology unlocks entirely new views of the cosmos.
It really is. And it highlights that discovery is absolutely ongoing. There's still so much more to learn, even in our own galaxy, which leads to a rather provocative thought actually pulled from the research itself.
Oh, what?
Given how rapidly these numbers jumped with Gaia DR2 and DR3, would anyone care to guess how many open clusters will be in the final Gaia catalog maybe a decade from now, when all the data is fully processed?
That's a great question to ponder. Will it be 20,000? 30,000? More?
Who knows? The universe, it seems, always has more surprises tucked away.